Can hear speaker. There's,
Can you hear me now?
no, the music's too loud.
Okay, put it down a little bit.
Yeah.
Is that better? Can you hear us?
Okay, much better.
All right. Yeah, so please scan and get yourself ready for Kahoot. Can I ask who's narrating? You are? Yep. Okay. Sorry, what's your name?
Yenza.
Yenza. Okay. Okay, so when we get 10 people, maybe we can start. We have viewer football, one here. So while we're waiting for enough people to sign in, just to double check, we're coming close to the end of the sem. We have just what, 2 more classes left. There's week 12 and week 13 left. Week 14 Wednesday, before our lecture, we have steps. So that means we need all of you to have your posters prepared. So the suggestion usually is to do it in PowerPoint or Keynote. You can set up your presentation slide as one large sheet in A0 size. It's recommended usually that you do it portrait style. Okay, I will give you a template, hopefully today, if I get some time to do it, which you can just clone and take down and reuse. And feel free to not use that template. It's pretty ugly, as a lot of things are in my group. So permit it as whatever you want, but you need to get us the PDF file so we can print it for you. Okay, then 2 Wednesdays from now, around 7 o'clock, you will come to, I think, I'm not sure yet whether they decided, probably SR1 in the other building. Okay, there'll be poster boards for you to tack your poster up, and there'll be food provided for you. Okay, so you don't have to worry about having no dinner. Okay, they'll give you a meal ticket, then you have to turn it in for your catered bento box or whatever it is. I think maybe they actually do it by buffet, but we had some problems with buffet where very hungry undergraduates would consume all the food and there's only like starch left. Okay, so I think they tried to like ration it out so it's not so terrible. But in any case, that will be the event that's going on. During that event, there are 2 things that happen. One is you get to present your poster. So, you know, that doesn't mean you have to be stationed there for 3 hours in a very crowded room with many, many overheated people. Okay, but it does mean that you get to spend some time presenting your work, explaining to your classmates what you've done, explaining to guests what we've done. And other classmates in other modules, like I think I alluded to before, there's another software engineering class doing AI, LLM stuff. So they're doing it from the application point of view. Okay, so they're also doing it. You may want to invite them to come look at your poster. Okay, so like I said, you're not spending all 3 hours standing there. I expect you to go around, look at other posters, chat with people, just generally try to have a good time. And when you're available, go check on your poster and see whether there are anyone who wants to do it. Okay, SOC students are generally known not to present very well, so this is more just for chances for you guys to practice. Okay, having a good time and talking about things that you care about. Okay. The other thing is there is a popularity contest during this event, which means you may have seen in the STEPS website, they list different tracks. Each track is a course, and you will be asked to vote by I think QR code or something, okay, to a form that says, tell me which projects you like from each of the different tracks. So it's expected you vote for yourself. I mean, who wouldn't? But then if you like other people's posters, please write them down. Okay. Typically, our undergraduates win this award. Why? Because our undergraduates know more people than our graduate students. Okay. So yeah, and larger projects tend to do better in the popularity contest. Again, for the same reason. Okay. So I will be there. I'll be going through all of your posters and giving some comments. Hopefully Michael will be around and also give comments. It really depends. Okay. So after that, on Friday, which is Friday, week 13, not Friday the 13th, but week 13 Friday, we will go out to eat for anyone who wants to after class is over. So 6 o'clock, we shut down. If we don't have any more discussion, we'll adjourn to someplace nearby here. Have drinks, not on me, I can't afford alcohol, but you can pay for your own drinks, but we can have a chance to just talk shop or talk non-LLMs content, have human intelligence instead of artificial intelligence for a while, and hopefully that's a bit fun. Okay, any questions about that? Yeah, okay. Yeah, Yisong.
So when is the poster due?
The poster is due, I think, by Monday of that week. Monday of week 13. Right. Friends, I think Yep. Okay, can you try log in again? If you're missing from the screen, we have only 7 people. Hopefully this time it's stable. Yusong, did you get your adapter back? Okay, it's good. All right. Okay, everyone in? That wants to come in? Okay, shall we start?
All right.
Anyone waiting?
Let's call.
Let's call.
All right. It's not. Okay. Nice.
Different word. Can I start? Okay. Of this next report up.
Can see the Kahoot screen.
I think that's issue the Zoom.
Oh dear.
But it might be lagging or something.
Can you see it now, Lawrence?
Yeah, all good.
Okay.
Nice. Yeah. So these are the benefits that visual-based LLMs provide over conventional LLMs. So as what Elson presented last week, these four are the right answers for eliminate all biases inherent in the data sets. I mean, we all know that it's not possible. Performs better common sense reasoning is actually an open problem that one of the authors for visual-based LLMs tried to propose. He said that the visual-based LLMs do not definitively perform better common sense reasoning. There are other methods out there that would help, but it's not visual-based LLMs. So let's see who's leading. All right, so we have HSB, Clyde, ALC, and this emoji thing, and YH. Next question, we have a multi-select question on the retrieval methods for retrieval-based LLMs.
Interesting graphic.
So chain of thought reasoning is actually a form of reasoning, so it's not really a retrieval method per se. Monte-Carlo estimation is just a statistical method. It's not really a retrieval method. Then we have we have new people. We have Yisong 3NM, HC, and laws. And next we have this is just a paper that I found linking chain of thought and retrieval-based methods. And next we have a question on double point question on best match 25. I think there was a bit of a discussion last week on this method. So yeah, this is So this best match 25 is actually just a metric to rank documents based on the terms. So it's more of a ranking matrix. The primary purpose is not really to score, but rather to use a score to rank the different documents based on how they will correspond to a given term. So red is semi-correct-ish. Blue is not really, because blue you're just comparing two documents, which would not really make sense if you're trying to use a term to compare with documents. Then green is just constant similarity. Yeah. So now we have PyTorch as the top, emoji thing as second, HC, not Yisong, and Clyde. Yeah, next question is multi-select and double points. So actually based on this, the authors for this paper actually proposed the yellow, green, and blue. So for green, it's known as random batching. For orange, it's based on the previously mentioned BM25, and for blue, it's just a longer segment-ish. Red is not relevant in this case. With red meaning that we batch consecutive segments from different documents, because that wouldn't make sense considering that the documents will be of different contexts altogether. Next, we have a true-false question. So in this particular in-context retrieval augmented language model, we only prepare a certain retrieved document before the input itself. And yeah, in the paper, the authors explicitly stated that they only implemented a specific fact to the query, such that it will produce, and that's the only so-called prompting that they did. They did not really do any training the model itself. They only added a particular fact that's relevant to the statement and asked the model to determine to do some QA from there. And we see that Yisong3NM has reached the podium. Has reached the top 5 then. And now we have a multi-select double point question on the data modalities used in Meta's image blind. It's yes. If you all will recall, this is the one where Prof asked Winston to build Yen LeCun for his little diagram. So actually all 6 are possible data modules used by Meta. So that was one point that they pointed out, that there was quite they were quite proud about being able to use all 6 in the image blind model. Okay, as we see that we have not Yisong3NM applied, but PyTorch is still leading the. Wow, actually I realized that PyTorch has a quite a domineering lead over the rest. 10K points versus 7K. So yeah, wow. This PyTorch, interesting, very good model. Yes. So the question we have, whether joint training of retrieval-based language models refer to training both the retrieval and language models concurrently. The training of both models concurrently, yeah. Yes, so for this joint training, it actually refers to training both together. It's just how often you will update the retrieval index, or whether you would, yeah. And now we see that we have Clyde and TY coming to the top 5. And here's the last question. The multi-select double point question on the possible reasons for test train discrepancy in joint training methods. So this was seen as one of the downsides for joint training methods, or rather it was one of the upsides. But there still exists test train discrepancy in these models. So yeah, so which of the following factors will lead to that? So actually, correct. Because this is more of a, because we cannot really eliminate test train discrepancy altogether. What the joint methods do is to try to reduce the test train discrepancy, but all 4 of these are still factors that lead to discrepancy. So the discrepancy will still exist, but you'll be at a lower magnitude when we use these techniques. So let's see who are the winners. So we have yes, these emojis as third, not Yisong as second, and PyTorch 3.0. Yes. PyTorch 3.0. Woohoo. As the first. Yay. Yeah.
Congratulations,
And
everyone.
now we have now pass the time to the team for this week's presentation.
Hello, I guess we're starting. Yeah.
Yeah, I understand.
So just to make sure everyone knows what a described document is, right? It's been announced, I think, by Warren on the general channel. You can go to that to help out the Scribe team. Okay, so Long, you can start.
Okay,
Yeah,
thank you, Professor. So, hi everyone. So this week we are going to present the multi-modal LLMs, and this is the outline of our presentation. We will first talk about the introduction to vision and language, and then we come to talk about large vision language models. And then the last section is we are going to talk about the other modalities. My name is Do-Sun Long, and I'm going to start the section 1, the introduction to vision and language. So at the beginning, I would like to acknowledge the tutorial from Lingier et alias, the recent advances in vision foundation models from the CVPR 2023. Now we are witnessing the vision and language models. Things are moving very fast. So from the LLM perspective, this year, now we have ChatGPT, GPT-4 from OpenAI, PaLM, Llama from Meta, Alpaca, Vicuna, and a lot of other closed source and open source LLMs. And from the vision community, now we also have some Dino to Stable Diffusions and Midjourney and so on. So things are moving and evolving very quickly. So what are the core research questions in the vision and language community? So probably first we pay the attention to the image encoder. Image encoder is probably the foundation of the foundation of the foundation of things. So what is the purpose of the image encoder? So its main purpose is how can we learn the image representations. So this one, the main purpose is consume visual data and then output for us some attributes or some representations of the input visual data. And then the second question that we have, or the research community has been studying for a very long time, is how can we extend the vision models with more flexible and also promptable interfaces. So next we can, when we're interested in consuming the visual data, naturally we also interested in producing the visual data, right? So now we come to the next module is called the image generation. And the very big research question here is how can we do the image generation, right? And then when there are something called large language models, then it come into the middle to play. So there are so there are several other research questions here. For example, how can we train multi-modal LLM, and also how can we train multi-modal experts with LLM? So here I would like to introduce briefly about some techniques that the community has been, the main techniques that the community has been using to pre-train vision and language models. So at first, on the top here, we have something called supervised learning, where we have the input is an image or multiple images, and then output can be something like a label. So the main advantage of this method is that we can learn the distribution of the image in a very specific way. So for example, if we apply the model in the image classification, let's say text classification, let's say the image text classification task, then we expect that the model will learn the representation of the text inside of the number inside the image. So it means that we can learn some very specific representation or very specific objects in the image in the supervised setting. Okay, so so there are several representative models that I think most of you already know. For example, AlexNet and also ResNet, and also modern transformer-based models such as VIT and SWIN also belongs to supervised learning. So we also have something called contrastive language image pre-training, and also non-contrastive image text image only. This one is image only pre-training. So for contrastive image language image pre-training, later on we will dive deeper into it. Basically, we try to train the model to learn to distinguish whether the text describe the image or the image actually can be described by the text. For image only non-contrastive learning, now for example, if we have an image, then we do some image argumentation, perturbation on the image, and then we train the model so that the model will output the two representations from the same source of image would be the same. And finally, the research community has also pre-trained the image by the mass image modeling style, which is originally from borrow the ideas from Bert in the NLP community. So now we will dive deeper into one of the most powerful one of the most powerful vision encoder in the both in the vision and the vision language community, which is the clip model, and it was pre-trained on the contrastive language image pre-training style. So contrastive language image pre-training style means learning the image representations from the web scale noisy text supervision data. So the advantage of this method is that, let's say if we combine to the supervised pre-training method, we need a lot of human labels to basically label the image. Let's say the image describe the number 4, then you need human to say that, oh, the label for that image is number 4. We need the label, right? But that one is very expensive, especially when we have very large model and we want to pre-train it on a very huge data. But for this contrastive language image pre-training method, we can learn from noisy text supervision. Instead of we need the exact labels. So for the training, basically simply using contrastive learning, which I will introduce later. And the beauty actually lies in the large scale pre-training, and surprisingly, the researchers have been showing that this method can be used to transfer to zero shot in the zero shot transfer manner. in for example, in image classification or image to text, image text retrieval. So now I will introduce the clip algorithm. So this paper, this model come from OpenAI, and it is one of the most powerful model in both vision and language community. So the idea of the algorithm is very not so very simple, but the idea is not complicated. Okay, so let's say now we have given a batch of n image text pairs, and clip is trained to predict which of the n multiplied with n possible image text pairings across a batch actually occurred in the reality. So let's say, for example, if I have two images, one cat, one dog, then I have two texts, cat and dog, then it means that now I have four pairs when I use cat, dog, cat, dog, right? So the model will try to predict which pair is the pair that appear in the reality. So the method is that jointly training an image encoder and the text encoder to maximize the cosine similarity of the image and take embeddings of the n real pairs in the batch while minimizing the cosine similarity of the embeddings for the rest of n square minus n incorrect pairings. So that's why it is called contrastive learning. So you may wonder why this such not so complicated algorithm invented. Like we need to wait until 2021 to see such powerful model, right? Because the algorithm itself is not so complicated. So the difference lies in the scale. So back in 2020, this idea actually was applied and pre-trained. People already pre-trained several models based on this contrastive learning strategy. For example, the paper called Vertex, or another paper, or another main motivation for clip is the paper called Convert. So this one stands for contrastive vision, contrastive visual representation training, I guess. So this one is the main motivation for the clip paper, where the authors, back in 2020, the authors trained this model on the medical image data set. However, this data set is only a few, like H00K samples, while in clip, OpenAI trained them. Basically, OpenAI borrow this idea, but trained on the web text, on the web text data set, which has like around 400 million pairs, I guess. So so the difference lies in the scale. So it means that the idea of clip actually appears before, where this paper is contrastive visual representation training, I guess. When they train with much smaller scale data set on the medical image data set, and they show the very promising results. But when OpenAI came to use the same technique, and they train with much more huge data set, like more than around 400 million text image pairs, then it makes a huge difference. So that's why clip and it can, and they even show that the model can be used for zero short transfer for other tasks. So that's why clip is so powerful until today. Okay, so what actually happens inside the codes? So you can see, for example, here we have the image encoder, here we have text encoder. So DI here is the hidden the embedding dimension for the text, and DT here is the embedding dimension for the DT is for text and DI is for image. And first we got the batch embedding from the input batch of image and input batch of the text, and then they do some normalize and then transform, basically to transform those embedding into the same space to say the same space so that they can compute the cosine similarity, because the image in the image space, text in the text space, so you cannot directly compute the similarity score, and they move all those into the same representation. The dimension is DE, and then after that they compute this one is the dot product multiply with the E something E. This one is E power T here is a temperature, and then after that they compute the cross entropy between the losses and the labels. This one loss I here basically is with respect to AC0. It means that they compute for each, it means that for each column here they try to compute the distribution on that column. So it means that on the column, and if we come back into here, column here actually represent the distribution over the image. So it means that the first loss I here is given one text and we have all the image. Then what is the distribution of that text over the whole image? Okay. So for loss T is in the reverse direction. So given all the text, one image, then what is the distribution of that image over all the input batch text? Okay. And then after that, they just plus the loss I and loss T and divided by 2. So basically first compute distribution based on the column, then compute distribution based on the rows. Then yeah. And here is what happened in the code. Okay, so so what are the advantages of CLIP? So CLIP can learn strong text pair representations. It can also learn from noisy data, and it has strong zero-shot transferability. And one of the most important reasons why it's still alive, it is still alive until today, is that it can be scaled very well. So this one is one text from the flip paper appear in CVPR 2023. So they say that flip is an outstanding example of simple algorithms that can scale well. So the simple design of clip allows it to be relatively easy executed at substantially larger scales and achieve big leaps compared to preceding methods. Yeah, so the main difference is the scale. Okay, yeah, so I think that's come to the end of my presentation. Any questions?
Questions about CLIP and all the other algorithms that came in from Long?
This shows like a symmetric loss function. Like, what do you want to copy for one image all the text and for one text all the images? How does that help?
Yeah, so so basically for one image you have a bunch of text. You want to know which text align with that image, right? So that's why you need to compute the distribution over all the text. And let's say in another direction you have the text, but you have the whole batch of images. So you want to compute distribution over the images. Yeah, and the two laws actually valid, right? Yeah.
So by combining the two laws together, then you can find out which incorrect pairing.
Not I can find out, they can find.
They can find out.
I did not innovate this one.
You just click on the slide and then you can use the cursor keys. Yeah.
Oh, sorry.
Yeah, you have to turn off the yeah.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Other questions? I think CLIP is an algorithm that everyone in our class should know. I mean, it's related very much to what we have been talking about in the other segments. Right, anytime we need to handle more than one modality, as we talked about last week, it's very important.
Yeah, okay. So if no more questions, then yeah, please next speaker.
Okay,
Thank you
thank
for
you.
the attention.
So do we have our next presenter?
Oh, yeah, yeah, he has the video.
Okay, so let's go to the next slide. So Liong, did he put a video?
I'm here to give a presentation about BIP2.
Okay, great.
BIP2 stands for Bootstrapping Language Image Pre-trained Model 2. This was created by the Singaporean Salesforce team, which shows that Singapore can actually create some well-renowned multimodal models. So what is
Yeah, the team in question is Shafiq's team from NTU. So he's part-time at NTU, but also Salesforce research in Singapore. And he's actually taken over Salesforce research NLP, and he's now in the West Coast. So actually we have a couple people related to that group here, like Minjers in my group, and she's also co-supervised with that group.
bootstrapping? Bootstrapping conveys the idea of starting with very limited resources. So BIP2 was trained with very limited resources. How did it do this? Well, it utilized off-the-shelf image models and large language models. If you look here, both the image model and the large language model have their weights frozen. And the challenge that the Salesforce team had to do was pass data between the image model and the large language model. To do that, they created QFormer. QFormer stands for Querying Transformer. So if you see QFormer's architecture, it is made out of an image transformer and a text transformer. The image transformer has a self-attention layer, a cross-attention layer, and a feed-forward layer. Together, they form one component, and many components can be stacked upon one another in the image transformer. The text transformer, likewise, has a self-attention layer and a feed-forward layer, but lacks the cross-attention layer. These two can be grouped together and form one component, and similarly can be stacked on one another. Let's look closely at the image transformer. Basically, the image transformer takes in query tokens, which is a set of learnable query vectors to extract visual features from the frozen image encoder. And the end goal is to have a set of learned query tokens. The cross-attention layer is connected to the image encoder, so the image encoder's data is passed into the cross-attention layer and interacts with the query tokens. For the text transformer, text is transformed into text tokens and passed to the self-attention layer. But I lied just now, saying that both of them have separate self-attention layers. Actually, the self-attention layer is the same across both transformers. In this way, the query tokens and text tokens can interact with one another. Let's look into greater detail at the flow of data in the Q transformer. So query tokens that pass into the image model, image transformer, and pass into the self-attention layer, while text gets broken into text tokens and passes into the self-attention layer. So they both interact, but only the query tokens get passed into the cross-attention layer and mix with the data from the image encoder. Next, they pass to the feed-forward layer and come out as learned query tokens. These tokens are passed to the fully connected layer, which shape the tokens to the LLM's input dimensions. And finally, the large language model has text that comes out as the output. So let's talk a bit more about vision in language representation learning. This is done by three methods: image text contrastive learning, image grounded text generation, and image text matching. For image text contrastive learning, we try to maximize image representation in text representation as image token pairs. Let's take a look at the self-attention layer in the model. As you can see, it is partitioned between query tokens and text tokens. Text tokens can only see other text tokens, and query tokens can only see other query tokens. This allows the transformer to generate image text pairs. And basically, they have to find the pair that has the highest similarity. So if a picture of a dog has the label cat, that will give a very low pairwise similarity. On the other hand, if the label of the image of the cat is a cat, it will give a very high pairwise similarity. Let's now talk about image-grounded text generation. This is caused by multimodal causal self-attention, which is very similar to the causal self-attention in LLMs, which is done by teacher forcing. There's basically some tokens that are masked in the attention layer. This helps train Q-former to generate text given input images. Inside the attention layer, only query tokens can see all other tokens, but text tokens can only see query tokens. This allows it to calculate the loss of the text generated from an image and then compare the text with the ground truth text of the image. Next, let's move on to image text matching. Basically, we're trying to learn fine-grained alignment between image and text representation. This is very similar to the text classification task that is done by encoder models. Just like the encoder models, binary classification task is where the model is trying to predict where an image text pair is positive or negatively matched. So for BLIP2, its training data consisted of the original BLIP corpus of 129 million images. This corpus is basically images with captions, and also the Liong 155 million images, which also have captions. BLIP2 also uses web images, and where CapFlit was used to create synthetic captions for them. If you look at the BLIP2 benchmarks, BLIP2 outperforms much bigger models in some benchmarks. If we look at the big Flamingo 80 billion model, it has 10.2 billion trainable parameters and 80 billion total parameters. On the VQA V2 test benchmark, it gives a score of 56.3, while BLIP2 using FLAN-T5 XXL has a total of 108 million trainable parameters, 12.1 billion total parameters, but gives a higher score, about approximately 10 more, 65, than the Flamingo 80 billion model. In conclusion, saving training costs using pre-trained image models in LLMs can give SOTA performance. So this ends my presentation. Thank you very much.
Hey guys, do you guys have any questions about what was presented? Step 2. Everyone's looking away. I guess that means. Okay, let's go ahead. Guanzhen, you ready?
Okay, so today I'm gonna talk about the LLM-aided multimodal reasoning. So okay, so this is the paper that I'm gonna cover today, the GPT-4 tools. And before introducing the details in this paper, we're gonna talk about some general types of multimodal reasoning frameworks. And they can be generally classified into three categories according to the large language model's role, according to a survey here. And large language models can serve as a controller, a decision maker, or a semantics refiner. So the paper we're gonna cover today is about the large language model's role as a controller. So we can first have a simple look at some examples about the different roles of large language models. So for example, in this research, they just let the ChatGPT to generate a sequential solution to a given task by calling the specific external tools. So for example, we can see in this task, it asks which is the main persuasive appeal used in this ad. So to address this problem, it will just first cause the text detector to extract the words within the image, and also use the knowledge retrieval to get the related knowledge about the three choices and some terminologies within the questions. And then they will do some analysis according to the existing information, and finally it will return the ultimate answer. So in this way, it is called as controller because it can learn how to use the tool. And also large language models can serve as a decision maker. So in many frameworks, to answer a given question, this should be, the pipeline is in a iterative format. So when to stop is a question. So at this time, the large language model can decide if the answer returned based on the existing information is confident enough or not. So if it is confident enough, it will just return the answer as the ultimate answer. But if not confident enough, they will just repeat the iterative process. And also large language models can serve as a semantics refiner. So for example, in this pipeline, we can get a lot of information about the image to do the captioning task according to the requirements from the user. But to make it, or to structure the information as a caption, they just use large language model to summarize all the existing or extracted information as a way that is expected by the users. Okay, so we have briefly introduced the three rules of large language model to do the multimodal reasoning. So we can now have a more specific look at this paper. So first of all, the novelty of this research is to distill the capability to select tools or to use tools from the ChatGPT to the other open source large language models. And just as we have mentioned that the ChatGPT has the capability to select the proper tools according to a given task. So generally, this pipeline consists of two main steps. The first one, they just construct a data set, and they just regard the answers from the ChatGPT as the ground truth when constructing the data set. And the second step is they just fine-tune open resource large language model to make it automatic tool selector. So they have done much work for constructing this data set, because generally there are three modalities in this task: the image and the tools, and also the user's input or user's requirement. So for the first step must be letting the ChatGPT understand the information input from the three modalities. So for the image content, they just represent the image or the visual information as the captions in the format of natural language. And as for the tool pocket, they just also use natural language to describe a set of tools and in the format as the tool name and each tool's using scenario, and also the arguments of each tool, and also the instructions on how to set the specific arguments. So after aggregating the input of the three modalities, they just got a prompt to input into the ChatGPT, and ChatGPT will also return the answer, including, do I need to use a tool to solve this given task? And if so, what tool I should use? And how should I set a proper argument for this tool? And these answers, they are just regarded as the ground truths of the data set. Okay, so but when constructing the data set, there is a problem. Is the ChatGPT has the bias because it just prefers to return yes when asked ChatGPT if I need to use a tool to complete this task. So to make the data set fair, they just supplement the data set with the negative samples and context samples. So the negative samples here means the situations that do not need the tools. And they do this by adding some samples from the existing data set. And as for the context samples, because we can see that when asked ChatGPT to generate a sequential solution, they will just return multiple used tools at one time. But sometimes maybe we need to let the tool selector to think step by step in many times. So they just supplement some context samples by breaking one answer from ChatGPT that needs to use multiple tools into the several samples. So this is a case like maybe here are two tools that need to be used to solve the given task. So in the context samples here, one of the used tools just be moved into the prompt part, and the answer part just becomes okay. I have got a question, a task, and I know that the first step I need to use this tool, and my answer is just what the next tool I need to use. Yeah. So as for the evaluation, they mainly focus on the tool selection. So they just evaluate the performance from 3 dimensions. The first one is the decision on if they need to use an external tool. And the second dimension is if I have used the correct tool. And the third dimension is if I have set the tool's arguments properly. And also they have got a final overall metric by aggregating the 3 dimensions. And as for the results, when they analyze their results, they mainly focus on 2 questions. The first one is, can the constructed instruction data sets teach the open source large language model to use tools? So to answer this question, we just need to see the results between the fine-tuned version and the not fine-tuned version of the same open source large language model. Just for example, we can see the OPT, and we just compare the first row and the second row here. We can see there is a significant improvement on the model's tool selection performance. Yeah, so the answer to the first question is yes. And the second question is, can the model be generalized to unseen tools after fine-tuning? So here we can see there are 2 groups of experiments. Here is the validation set, and here is the test set. The validation set here means when we evaluate the model, we just ask them to select tools that have appeared in the training set. But as for the test set, we just also there also may be some tools that not used to appear in the training set for the models to select from. So, but we can see from the results that both in the validation set and the test set, there is a significant improvement after fine-tuning the large language model on our constructed instruction data set. And that is to say that the model can also be generalized to the unseen tools after fine-tuning. They also have done some ablation studies. So the first thing they have tested is if the the multiple steps used to construct the data set are meaningful and useful. So the IC here means if we need to provide an image content in the data set. And the CS here means if we need to add some multi-turn context samples into the data set. And the NS here means the negative samples, which means some situations that do not need to use the tools. And from the result, we can see that almost each of the module has played an important role in this pipeline. But I think one interesting discovery here is after introducing the negative samples, it seems that there haven't been a quite significant improvement here, maybe just 2% or 3%. So I also have seen the data set distribution in their appendix to find out the reasons. So this is the distribution of the training set, and the purple section means the proportion of the negative samples. And here, similarly, here is the distribution of the test set, and the purple section means the negative samples. So we can see that although in the training set, the distribution is relatively fair, but in the testing set, you can see there is just a tiny proportion of the negative situations. And that is to say, even though I haven't used the negative samples to train or fine-tune the large language model, even though I just treat all the negative samples or all the situations that I don't need to use the tools as the situation that I do need the tools, there can still be a quite high accuracy as for the tool selection. So I think this may be the reason why the negative samples do not show quite significant effect on the performance of the fine-tuned models. Yes, and they also do an ablation study about the model size. So they just use the vicuna with 7 billion parameters to fine-tune, and also use the vicuna with 13 billions. But we can see that even though there has been a significant gap between the number of the parameters of the two versions, but this just can lead to a quite similar performance in terms of the tool selection. So this also indicates that there is a probability that we can use the large language model with lower scale to be trained as a tool selector. Yeah, so but from my view, there are also some potential weakness for this research. The first one is the whole paper only focus on the consistency between the open source large language model and the ChatGPT. And that is also to say, like, they just regard the answers from the ChatGPT as the ground truth. But there is also a probability that ChatGPT may incorrectly select a tool in practice. And the second weakness for me is they only report the results of the model selection, but do not evaluate the quality of the answers, which means, okay, now I can select the tools consistent with the judgments from ChatGPT, but we do not know if this can benefit the further tasks, like specific tasks like captioning or reasoning or something like that. Yeah, so this is my presentation about this paper. Any questions or comments?
Comments? Can we go back to your success rate?
Yes.
Yeah, so here it seems like the language models are quite different in terms of performance, especially Llama doesn't seem to do very well and Vicuna does. So yeah, did the researchers report any findings about why Llama doesn't do very well?
Oh, I'm afraid they do not expose the reason why they differ so significantly.
Okay, I mean, I think some of you have used Llama and Vicuna as well. So if you have any comments about what you see from the performance of these different language models, you can also say something about that. I think it's good to know they're not all very comparable. Their algorithms are different. Their training data is definitely different, right?
Yes, so for me, maybe not an accurate answer.
Yeah.
A deduction is I think when I use different kinds of large language models, different models have their own preference in terms of the task or prompts. So from my view, maybe Llama, maybe due to the training process or the corpus used to train, maybe leads Llama not to perform that well or not that suitable to this tool selection task.
I think it is probably mainly due to the following instruction
The instruction.
ability. Yeah, because Vicuna was trained on top of Llama and on the instruction by tuning data. So it has a better ability to follow the instruction, but probably Llama may not understand very well, especially if you don't use the chat version of Llama, then yeah, it may not understand it very.
Yeah.
This is my guess. I mean, just now I didn't pay attention to the task, so I don't actually know what is the task, but let's again.
I think the down to your Shenlong.
Long.
Shenlong, yes, it's to Shenlong's like point, right? Like I think Llama, I don't know if there is the alpaca version, but I think for the alpaca version, right, they are fine tuned like specific instruction prompt. So if let's say the prompts over here are different, right, then if it's not in alpaca prompt format, then of course it will be worse compared to like the.
Yeah, I do agree with you because like different large language models also have their own preference in terms of the prompts or the instructions. So for some cases or some formats of the training data, for some large language model, they may understand better, or for some they may just cannot understand. Yeah, I do agree with your opinions. Yeah. Any other questions?
Can you go to the success rate computation? Computation. The formula for it. So it's proportional to SR times SRAT. You had one where you had the formula for the computation, right?
Oh yeah, here.
Yeah. So what do you guys think? Do you think this is a good evaluation formula for this success rate? So they're saying that success rate is proportional to these three components, right?
Yes.
You just multiply them together.
Yeah.
Just multiply instead of add. Because usually when you look at like other losses, right, when they proximity losses, they usually add them together instead of multiply. But over here they multiply all the losses together. Like this is real arguments multiply the action multiply the plot.
That's the rate.
Oh, so the rate multiply.
The rate multiply makes sense.
Yeah, why is it multiplied? So Long, do you want to say? It is correct, but I want you guys to think about why and whether you agree with the balancing. Specifically, it says that all three of these factors are equally important.
Yeah, so let me try to explain in a very intuitive way. Let's say I have a coin, I flip the coin, then my successful rate would be 0.5. If assume that I have a fair coin, but if I flip the coin twice, then I should multiply 0.5 with 0.5 as the successful rate. I define successful as to flip the times I got the head. Yeah, so something like that. When success on this one, also need probability of success on another one, then it is the final successful, something like that. I guess.
So these are all prerequisites, right? You need to have a successful rate of thought. And if you need the tool, then you need to know which tool name to call. And then for the tool name, you need to know how many arguments to use, right? And then what are the arguments that you need to put in? So because we need all three of these things to be correct, then you multiply all of them together.
I guess I haven't read the book, I also did not buy it.
Yes, so from my opinion, maybe if we need to multiply them or if we need other indicators, may depends on two factors from me. So the first one, if the three dimensions are equally important. So maybe if they are equally important, we can just assign them as the same weight. But if maybe one of them is more important, we may just give them a higher weight in the final aggregated metric. And the other perspective from me is maybe the variance on different dimension also is important. For example, maybe just the successful rate, the highest and the lowest, maybe just there is just a difference on maybe 0.1. But if the successful rate of the arguments, the highest and the lowest, there is a gap of maybe 0.9. So at this time, if we just simply multiply them, maybe we cannot just simply regard them as the equally important because their variance is different. It is, I'm not sure if it is correct, it's just my own opinion.
Okay, yeah, I agree. I think it's important to think about, I mean, when we think about the overall success rate, definitely all three of these are prerequisites, but whether we agree that all of them are equally important and how to balance the interpretation of how well the models do when you go back to the slide with the actual performance measures, right? Yeah. So in particular, the SRT, right? The first column is easy, right? It's either yes or no. So this is a binary classification task. And seems like it's fairly easy to do. But then naming the arguments is the hardest to do, as we can see from these slides, right? Okay. Any other comments? Okay, I think tool use is definitely something that is picking up. I think a lot of people in even my group are thinking about tools and how they can be used and how they can be positioned as part of a probabilistic or generation guideline pipeline where the LLM is doing most of the controlling parts. Okay. Okay, thanks.
Yeah, thank you.
Hello everyone, today I'm going to introduce this paper, PALM-E, an embodied multimodal language model. So first, let's talk about an important question. So what's the task of this paper want to address? What kind of task does the paper want to address? So as we all know, that LLM have some strong reasoning and inference ability in textual space. So the problem is how to achieve the inference in physical world. So here is an example. So human can give an instruction, bring me the right shape from the drawer. Then after getting these instructions, LM should complete the task planning of this task. First, the rabbit need to go to the drawer and open the drawer and take the right shape out of the drawer. And even if the rabbit can be disturbed by human, it should bring it to the user and put it down. So in this process, the LM should have some visual perception ability. LM should understand the environment and perceive the environment. Besides, the LM should make a decision on some long horizon task. For this task, it requires multi-step. Second one is the most important thing is the inference is not in the physical world. The inference is not in the textual space. The inference is in the physical world. So the question is how to achieve the inference in physical world. So as we all know, LM have been pre-trained on massive textual data. And in this textual data, there are a lot of representation that it can be used to describe our physical world. So there is a connection. So the problem is how to establish the link between the words in the textual data and the perceptual modality in physical world. So a simple method will be directly introduce some new perception modality to the language models. So how to introduce new modality to pre-train language model? So PALM-E have given such a solution. So first, we need to get the embedding vectors of different modality. For image, we can just use vision transformer to get the embedding vectors of image patch. But for other modality, we can design our own encoder to get the embedding vector. And then we can directly insert this new embedding vectors to the language embedding space. So after that, we can get the multimodal embedding vectors. And then we can end-to-end train the whole model on some multimodal task. In this way, we can introduce a new modality to our pre-trained LM. So this is the new modalities in PALM-E. The first one is some state estimation vector. such as the pose, the size, the colors of different objects. The second one is use vision transformer to get the embedding vectors of the image patch. We split the image to some local patch and get the embedding vectors through vision transformer. And third one is object-centric representation method, which means first we will apply our object-centric mask on image, and then we will use vision transformer to get the embedding vectors. And the last one is about object-centric representation, which means we will use some representation vectors in 3D constructions, and then mapping this representation vectors to the language space. So after introduce all of these modalities, the next questions, after we get this embedding vectors and insert this embedding vectors to language space, the next step is use a pre-trained language model to generate or to predict or sequence of token. So for different tasks, this token have different meaning. For robotic tasks, this sequence can be the task planning of different tasks. But for vision language tasks, the token can be the answer to the given question. So, and for the model training, the model have been co-training across different tasks. The model have been training across 4 types of tasks, and 3 of them is related to robotics. The first one is a mobile manipulation. So the robot needed to move in the room and grasp some object. And the second one is about the pushing action in the table space. And the second one is about task and motion planning. And the last one is a vision language task, vision question answering. The LLM should give an answer related to a question and the image. So this is the training process. And for the training strategy, there are 2 types of training strategy. In the first one, they will train all components, including the vision transformer and pre-trained LLM. So in this way, they want to improve the model performance on some multimodal task. And the second strategy, they will freeze the LLM and only train other component. So in this way, they want to retain the language abilities of pre-trained LLM. So finally, let's go to the experiments. First, they evaluate the performance of PaLM-E on different tasks, on vision language tasks, and on inference tasks related to robotics. It can be seen that training across different tasks can improve the model performance compared with training separately on different tasks alone. So after co-training across different data, the model performance can be improved on vision language tasks such as vision question answering. The model performance on inference tasks related to robotics can also be improved. The performance on task and motion planning have been improved after co-training. So the second experiment is how to retain the language abilities after training on multimodal data. So they compare the performance of PaLM and PaLM-E. So PaLM-E is trained on multimodal data. It will lose some language ability. You can see the performance of PaLM-E is not as well as PaLM as on some language task. But we can also find an interesting thing that by increasing the model skills, can lead to less forgetting, which means if the model have more parameters, after training on multimodal data, the model will lose less language ability. The model will retain more language ability. So if the model have more parameters. So finally, get to the conclusion. First, we can just inserting some embedding vectors from different modality. This is a feasible solution for multimodal LLM. Second one is co-training can improve the model performance across different tasks, including the robotics task and the vision language task. Second one is increasing the model skills, increasing the model parameters can be a feasible solution to help the large language model to retain the language ability after training on multimodal data. So that's all about my presentation. So there are any questions?
Thank you. Questions? Nick first.
Yeah, go back to the slide where you showed there were 3 types of visual embeddings. Do you mind explaining what are they, and at the same time, did the authors do any form of ablation studies to justify why all 3 are needed? They have no ablation study about the sensor modality. They introduce this modality just to make sure that there are enough modality to help the model to run some general policy. They just want to show that they can cover different situations. So there is no ablation study according to the modalities. I'm trying to understand how these 3 are different. So I assume the first one is just raw image, and the first one is not raw images. First one is a vector, some vector.
about the position, such as the position, the size of objects. It's just some vectors. And the second one, you just use vision transformer to get the image embedding vectors. And then the third one, you will apply a mask. The mask is object centric.
To extract the object, and that's.
Yeah, to extract the object.
And the last one.
The last one is they use some representation vectors in 3D construction, which means this image will be pre-trained on some 3D construction task. And in this 3D construction task, we can get the representation vectors of the image. So they will use mapping this representation vector to the language space. This is the last one.
Okay. Other questions? So the symbols here, maybe you can clarify a little bit. What are the Greek letters that you're using here? This is from the Palmy paper itself, right?
Yeah.
So do you just want to describe it? Because I don't remember whether you covered it in your presentation.
So you mean the modality of different models?
No, the different Greek letters here, what do they stand for? Does everyone know? One is an embedding.
Yeah.
And then I forget what the other one is. I copied it from the paper.
I have one question. So what is the interesting of this paper?
Yeah, I think the interesting of the paper is he used a simple method to achieve the multimodal LLM. He just inserting some embedding vectors from different modality. So in this way, he can achieve just inserting some embedding vectors from different modality. Only in a simple method, they can achieve the multimodal LLM with on a pre-trained LLM.
So okay, so it means that just integrating the embeddings from other source of model inside the LLM.
Inside the LLM.
And that's the main selling point.
I think this is the most interesting because
okay,
maybe we don't believe it. It's a simple method, but it performs well as experiment results.
I believe it because the point is there are a lot of previous work already did it. So let's say if you may know the model for VLT5. So what they did was that they also first put the image into some object detection models to output some embeddings of the objects, and then they feed all those embeddings. So we can consider those embeddings as the embeddings of the image. Okay.
Yeah, the image.
T5 model, and then they pre-train. And then they show that it works very well. So what is the difference between the two?
Yeah, but it can also be sure that they will freeze the AM, but it also perform well. It can freeze the AM if the parameters of the AM is enough. So he can freeze the LM and only train the vision transformer.
So you can freeze the LLM and only train the vision transformer. But yeah. I thought that just now you introduced that they train the model in 2 stages.
Not 2 stages, two methods, two strategies.
Methods.
The first one, they will train all components. In the second one, they will freeze the LLM.
So okay, so how are the effects of the 2 methods?
Yeah. So for the first one, you can see the performance. If you freeze the LLM, the performance of the whole system will not as well as training the whole model.
Which line? Oh, okay, LLM.
Yeah, you can say LLM free.
So maybe you can use the laser pointer.
Yeah. So this one is LLM freeze.
Press on the keyboard. L. Letter on the keyboard. There you go, the laser pointer.
Wait.
Press the letter L on the keyboard.
Yeah.
Oh, okay, thank you. So this one is the 2 guys they are fine-tuned, and this one they are freeze the LM.
I see.
And I think if this strategy have been used in other work, other research, and think another important thing is the co-training in this model. In this model, here we have co-training across different tasks, across robotics task and the vision language task, and the co-training can improve the model performance on both 2 tasks.
Yeah, I think maybe the main selling point is it is for Google.
Yeah, right. Yeah.
Okay.
I think that's part of it. Definitely when you have a state of the art and it's trained on by a large corporation, it's much more likely that people will pay attention to it, for sure. I think Long is right to question the interestingness of the paper, right? I think you're asking, well, why is this so novel? You know, you just take the embedding and you stick it inside of the input space, and you just hope for the best. And with enough scale and with enough interleaved training from code training on 2 different tasks, you get better results, right? So yeah, maybe it's also interesting to think about, okay, since they did this is sort of really like very low-hanging fruit. You just get an embedding any which way you can, stick it into the model, and then pray that your H100s do a good job.
Yes.
And then you get good results, right? So if you were thinking like a scientist, like how would you go about improving the model structure and like using scientific techniques to see whether you can get a better result than this? Okay. Any other questions for you, Yuhong? Okay. Yeah, thanks so much. Let's give a hand then. So how's this section working? You have 3 of you are all.
No, this is not true. It's like we split it into different papers. So we have 3 papers for this.
All right.
So everyone, I'm Warren, and I'll be talking about Any-Modality language model today. So this is a table of contents, and I'll just go through like a brief recap of last week's lecture because it's relevant. So last week, Winston shared about image bind, which is an embedding model that works with multi-modal inputs. So image bind combines pairs of multiple modalities like images in another modality to create a joint embedding space for all the modalities. So hold this thought for a few slides. This will be relevant later, but I'll share more about like multi-modal LLMs in general. So most of the previous speakers were talking about integrating vision LLMs with text. So you have like Blip, Lava, like Flamingo, and GPT-V. But however, this is a more rare case, but there are also LLMs that can take in inputs from multiple modalities. And this is more rare. So like Panda GPT can take in multiple modalities, or NExT-GPT, which is what our next speaker is going to be talking about, no pun intended. So AnyMAL is a more recent addition to the latter, and the authors claim that it can understand any modality given to it. But it's not open source yet, so we have to wait until it comes out. Yeah. So introducing AnyMAL. So it can understand any modality and uses Llama as the backbone model to actually, as well as multiple encoders to handle multiple modalities. So like you have Clip, Clap, and all the other encoders to handle like audio, images, and other modalities. And most of their success, right, is attributed to 2 things. Now, one is modality alignment, which I'll go through later, as well as multimodal instruction fine-tuning. So now we talk more about the pre-training part or the modality alignment part. So what exactly is modality alignment? Well, the high-level idea is that it's used to create a joint embedding space. So before I actually go on, right, does anyone want to guess why we need this joint embedding space?
I mean, ultimately, we need align like which is which. I mean, like if it's text and image, we need to do some form of alignment.
Yes.
Connect that together.
Correct. So that's really the reason. And I find this very relevant to like, I think our discussion in the past weeks when we talk about like subwords and tokenizers. Because the thing is that if let's say you have an LLM train or a specific subword set, right? If you tokenize using a different tokenizer and you feed it to the LLM, it might be able to process like the vectors, but it won't be able to understand like the word vectors because it's from a different set of subwords. So it's the same thing here, but we just extend this concept to multimodality. If let's say you have images, right, and you feed it to like a LLM that was originally trained on text, it might not be able to understand what are the images and how to link it back to the text. So therefore, we need to join and align the embedding spaces together so that we are able to actually relate all the text to different modalities and link them back. So now I'll go through how it works. And first I'll use the laser pointer. Here. So firstly, right, this is our raw data, which is the image, videos, and other kind of raw input data, of multiple modalities. And we feed into an encoder like Clip or Clap or any other encoder. So now we have our embeddings. So ultimately, we want to align these embeddings to the word embedding layer. So to do that, we have a projection layer, which is usually a linear layer, but in some cases, they use different kinds of architecture that I'll explain in the appendix later. So we want to align both of these together. And how they do is that they use this formula here, which I'll explain later. Ultimately, you just need to know that you take all these embeddings and then you feed them to Llama V2 and you try and predict you try and generate a text caption, and then you see how close it is to the actual label given. So this is related to the first formula here, where you want to predict like given a certain modality, what's the probability of generating the label text caption? So this is basically what the objective that the position layer trains to align everything here. So on the right-hand side, you see something similar to like the perplexity formula, but it's more like the joint distribution. And what that basically means that the next token or the next piece of, or the next like word generator, right, will be like will be related to like the previous tokens that was generated by the LLM, as well as the previous modality tokens given to it. So this is just like similar to like your normal perplexity or your normal like joint distribution like objective, but you just extend this to a multimodal sequence. And the high level idea to actually like that this is trying to solve is that given like a specific caption, right, how do I maximize this probability to get this caption out when I have all these tokens from different modalities and different texts? And if I can maximize this probability, I will be able to align my embeddings together. The second formula is just explaining like this part, the projection layer and the modality encoders, because Z modality just means that it's a multi-modality token. So that means that you feed in your raw data into an encoder, and then you align it through a projection layer. And then after you align it, right, you get your token, which is from this joint embedding space. So they call this token Z modality to differentiate it from like a normal text token. So now I go on to something a bit more for like scaling. So actually they wanted to like scale their training up because they were using 70 billion llama. So to scale the training, they quantize the LLM to both 4 and 8 bits. And also they froze the LLM and only train the modality encoders and projection layers. So this led to their method achieving the same throughput as SSDP or fully sharded data parallelism while achieving using half the GPU resources. And the most impressive thing to me is that they managed to pre-train Llama V2 70 billion as well as the encoders and projections on a single A100 80 gigabytes with batch size of 4, which is quite impressive because if you see similar works, right, usually they'll use like 8 times A180 GB to train like similar parameters or even for longer periods of time also. So this is quite impressive to me. So now I'll talk a bit more about fine-tuning. And really the objective of fine-tuning is to really improve on the model's multi-modal reasoning capabilities. So the authors were having this hypothesis that if you train it on more data, it will lead to better reasoning, especially if you give it high-quality responses. So what they did was that they updated whether we should fine-tune the large language model on multi-modal instructions, which is their own custom dataset, using QLoRa. And to do this dataset, they concatenated the text and the modality tokens together, and then they upload this in the results. So they created 2 datasets also updated on that. So firstly, they have manual annotation, which is like our usual standard datasets we use. That means we collect data manually, and they have very strict constraints on the data. So it has to be strictly multimodal. So this means that if you give it a prompt or query, it cannot be answered without the multimodal context. You have to combine both in order to actually answer the questions given. This is to ensure that the models are able to use the multimodal context effectively. They also use synthetically generated data, like the one in GPT-4 tools. So, but instead of using GPT-4, they use open source models instead to generate 150,000 examples of question-answer pairs on various domains. And this is done by representing the image textually to generate these pairs. I won't be explaining this because of time constraints, but it was actually inspired by the Lava paper. And I have this slide over here that leads to the explanation of how they actually did it. So finally, I'll talk about the results. So the main focus of experiments and application by the authors was for these 2 tasks, multimodal reasoning as well as captioning multimodal inputs. So the reason why the authors chose these 2 tasks is because for multimodal reasoning, they wanted to check whether unified embedding space had any impact on improving the model's reasoning, which means that if I do not align all these embeddings together, will I get a worse performance or will I get a better performance? Another thing is that when they also tested on captioning, which I believe that it evaluates the level of alignment between the embeddings directly. Because if let's say you want to find out, let's say you want to make a caption of let's say an audio text or like maybe like an image, you need both the text embeddings as well as the current modalities embeddings to be well aligned together first before you can accurately like caption out that specific modality. So therefore, I think that's why they chose this task. So here are some results, and I'll just highlight the first part. On the left-hand side over here, we have image captioning results. And on the right-hand side over here, we have the win rates for the reasoning results. And I'll explain the left-hand side before I go to the right-hand side first. So on the left-hand side, you can see that AnyMAL 13B and 70B, right, managed to achieve around 99 to 95%, which is much better than the rest of the models given here. So there's an interesting observation here, which is because that even though like both of these models are less than maybe either fixed 80 billion and also some of the models here are I think larger than the AnyMAL 13 billion, but AnyMAL 13 billion can still outperform most of them. So they believe that the capability of the LLM or the skill of the LLM has less impact on the captioning performance, but compared to like the dataset quality as well as the modality alignment we talked about just now. Because not only did AnyMAL 13B beat like AnyMAL 70B, also beat other models of similar size as well as larger size than it. So they believe that the pipeline of having the modality alignment and dataset quality actually directly impacts the performance more than how much parameters the LLM has. Then over here on our image-based reasoning, we can see that over here they ablated how to do the fine-tuning. So we can see 3 types of AnyMAL here. Number one be AnyMAL without any fine-tuning. That means they take the pre-trained version and directly evaluate them on the task of image reasoning. The second one will be synthetic data only. So that means they only train the pre-trained version on only synthetic data and then try to evaluate it using that. And the last one would be combining both the manual and the synthetic data together and then fine-tuning AnyMAL on the data set. So as you can see here, the win rate for like the combined data set, which is fine-tuned on, is the best out of all 3. And I think this is because you're giving it more data, and because of that, it's able to understand more visual concepts, as well as also improve its reasoning. So the author's hypothesis that giving more data to improve reasoning is correct. So now we'll look at like the performance of AnyMAL across multiple modalities. And first, I'll talk about the image-based modalities, which is image and video. So you can see that AnyMAL on images itself, right, are mostly state-of-the-art except for some of the QAs, but it loses to Bleed V2 for most of the video QAs. And the authors wanted to point our attention to this small fact, which is that they also updated based on like which image encoder they're using. And they found out that if you use a larger visual encoder, you lead to better results. And this is because I feel that QA is like a knowledge-intensive task. So if you have with a larger encoder, you can better represent your image embeddings. So it will lead to a better representation. And because of that, by using a larger visual encoder, it will lead to much better performances. So you can see that they use the same thing here. They compare intern video with like VidG, and they still found that VidG is able to beat intern video consistently. So which means that when choosing an LLM for like an image QA task, right, especially when it's multimodal, you want to actually have like a large enough visual encoder to actually accurately represent the representations of the image so that your LLM can perform better. They also do the same thing for audio, and they found out that unlike image captioning, audio captioning requires reasoning. So therefore, the 70 billion parameter actually shows better performance compared to 7 billion and 13 billion parameters, because reasoning ability is crucial for audio caption generations. Without this reasoning, it won't be able to actually understand the audio as well as give a caption for it. One more thing over here is that just to clarify, why did 13B like beat 70 billion on the image captioning performance? Well, the issue is not with the model itself, but actually with it's the artifact of the benchmark itself. Because for CIDR, if you have a very long generation, it will actually penalize you for having longer captions. And Llama 70 billion is a very verbose model, so let's give very long captions instead of, unlike 13 billion. That's why it was penalized and got a lower score compared to the 13 billion parameter model over there. That's why you see 13 billion outperforming AnyMAL 70 billion. So now I'll continue on. So what are the key takeaways from this paper? Number one, scaling. The 70 billion models commonly perform better than the 13 billion and 7 billion variants. And I believe that this is due because of the inherent capabilities for the model to reason, as well as the knowledge of the model. So this demonstrates the importance of actually scaling LLM parameters in vision language pre-training, something that is not talked about in many papers. And the authors also pointed out that this is not talked about by a lot of papers. The next thing is also, this is like one of the first papers to actually reason directly from IMU data or motion data. So this task has not been accomplished by previous multimodal LLMs. Even if in the next speaker's MotionGPT, they did not use IMU data directly. But this one uses IMU data, and then if given like some reference images instead of the IMU data, it's able to generate like something that combines both of them together. And over here, I have more of like training losses. You can see that scaling is very important. This is just the first point, because even though the authors updated on the different hyperparameters to improve the performance of the 30 billion model, none of them actually compared to the 70 billion model. So therefore, scaling is a very important thing. Now I'll go on to like, I think the most important question, because this is more of an applied use case. So given multiple modalities, right, can AnyMAL actually take in all the modalities and understand all of that at once? Well, the answer is yes, it can.
Don't understand this. How many
modalities can we add? Yes, it's a meme.
Okay.
So you can put as many as you want inside.
And
so
the answer is always yes.
Yeah, the answer is always yes. Scaling leads to yes. So example problem will be over here where we have two different modalities. The first one is like IMU data of biking. So someone is cycling, and second one is the San Francisco Golden Bridge. So by combining these two modalities together, AnyMAL can actually output quite a good answer. It can say it identifies that it's pedaling along somewhere. It also identifies that it's the Golden Gate Bridge. So it says pedaling along the San Francisco Bay, taking breathtaking views of the Golden Gate Bridge. So something that the authors didn't really explicitly say, but something I realized that actually for AnyMAL, it's also able to identify locations very accurately. Because in most of its other generations, right, that the authors put in the paper, it's also able to identify places like a river or maybe even the name of the river. So I feel that's quite interesting. Lastly, for figure 5, right, it illustrates how we can set this out at inference time. So as you can see over here, most of the architecture here is very similar to what we do for fine-tuning, but this is for inference time. So we're not actually training the model, we're just running it to get the output. That's why over here you see that this curly line here, right? It's just saying, it's just the autoregressive nature of like a decoder. So basically, because you know that a transformer decoder, it takes in like the previous tokens to generate the next token. So that's what the curly line is. That's what the curly line is trying to explain. It means that given the previous tokens, I want to decode and generate the next token out. So by using this setup, right, you can actually take in multiple modalities, which is something I think a lot of different other multimodal transformers haven't done yet. Like even for GPT, I think it can only take one modality at a time, either image or sound. I think there hasn't been any like upgrades to take multiple modalities yet, as per my knowledge. So what's the limitations? Well, the authors cheated. Basically, they did not test on every single modality, like point clouds or depth maps, like what we saw in the image bind paper. But they claim that this architecture is flexible enough to work on these modalities as well. Something that we need to find out for ourselves after they open source the model. And there's still a lack of robust grounding. So what do we mean by grounding? Grounding means that even though you're giving it like both the multimodal input and the text, it does not give the same weight to both. It means, let's say you give it an image of a chair and you say, I would like to sit on the table. If you explain more about how to sit on the table and like sitting down on the table rather than linking it to like the image of a chair given to it. The last thing will be that if you do not train it on a large enough data set, it will also cause it to have limited understanding of visual concepts. So let's say you only train like the AnyMAL on only images and only on tables and chairs, you do not train it on anything else. Let's say I give you a picture of a bag. It will think that the bag is a table or a chair instead. So one way to actually ameliorate this is like last lecture, we talked about retrieval augmented generation. So by having like a vector database of images, we can retrieve the image and the caption, and then tell AnyMAL, yeah, this current image is actually called a box or a bag. Then from there, you'll be able to understand and able to generate out something that's more relevant. So yeah, that's my conclusion. In conclusion, AnyMAL is like a flexible multimodal model that can work on multiple modalities, and scaling is very important in multimodal works because the reasoning and knowledge in larger models affect the performance. And I don't know from my last point, so like Lauren Ipsum. So does anyone have any questions?
Let's
Yes.
thank our presenter first.
Yes.
Yeah, so can you compare to the architectures like
Which one?
the fine-tuning one?
Oh, fine tuning. Let's see. Here, right? This one.
Yeah, so I'm trying to understand why
Which part?
only LoRa in the instruction part.
Oh, okay, because like for the LM, right, there's very large parameters, it's about 70 billion. So that's why I do the LoRa there. Compared to like the modality encoders, right? I have not read the specific papers for each of the encoders, so I cannot give like a very good answer here. But I estimate that at least these are significantly less parameters than the large language model, right? So therefore, I think compared to like the training on the large language model, like it'll be more negligible over here when you're fine-tuning. And also another thing is that I think you really pre-train most of the projection layer and everything, because in the pre-training, you're only aligning all the embeddings to each other. But in the fine-tuning, you're fine-tuning the entire thing. So I think that most of the computation is done in like the transformer there instead of like all the encoders, because you're not really updating that much really. You've done the updating of the alignment in the pre-training phase. So for the fine-tuning phase, you're more of just concerned how to improve the model performance, and therefore most of the updates will come from the transformer itself, and therefore we put the LoRa there because of number one, you are updating that the most, and number two is also because that's where most of the parameters are located.
Yeah, but the point is, let's say now if you add some adaptive parameters,
Okay.
then you should add for
all of the values.
Yeah, all the layers, or you can add for only few neurons. So in this case, they are trying to add for few neurons, or they try to add for the whole layer.
I think for the QLoRa part, they probably just added it for like every single layer for in the transformer. But because I think one more thing is that this like this part before the Llama V2, the projection layers and modality encoders, I think those are kind of like modular. You can take them out and put them back in. It's like, let's say I run it in this model, then it's like a separate model. It's not really the same model altogether. You're training everything in one shot, but there's still separate models. So let's say you have like clip, right? And then you have the llama, right? The clip itself, I don't know whether clip supports LoRa, I'm not so sure, but you have the clip and the llama, you can always take out the clip. The important part is the llama has the LoRa, right? So because for the encoders, I think you can substitute the encoders with each other. It's plug and play. So you can remove clip, you can put back clap or something like that.
I mean, my question is whether the LoRa there will apply for all the instruction, image, video, audio, request, response, all those embeddings, or just the instruction.
Like okay, I get what you're saying. So like the LoRa, is it? Like, because is it only on the instruction side or the okay, the LoRa is for the entire transformer. It's not, it doesn't depend on whether instruction, response, or request. Because the thing is that instruction is just a system prompt. You can't selectively say I just do LoRa for instructions. You can't do that. So the LoRa should be for the entire llama.
They can do for some neurons only like fixed window size.
Yeah, I don't think they really consider that because they just use like the fixed Q LoRa for Hugging Face. They say in the appendix they just plug and play a Hugging Face. So I think it's for the entire model. Yeah.
Okay.
Yeah, I think the graphics is a bit
positioned
bad.
very well, right? It's used to sit over the instructions, right?
Yeah, a bit confusing. Yeah. Understand.
So so my second thing is, can you come back to the weakness?
The limitations.
Yeah.
Okay.
Yeah, I think the authors actually claim something makes sense. I mean, they say that actually they may not test on other modalities, but in here they only say that this architecture is flexible enough. Yeah, they limit their claim.
Yeah, flexible enough.
So it cannot be wrong, right?
That's true. The best correct is technically correct.
Okay, that's all.
Okay, anyone has any more questions?
Yeah, Nick.
Okay, Nick.
Yeah. Can you just go back to the part about understanding locations. Can you repeat that part?
Understanding which one?
Locations. Is that something I
okay. So like you mean like this part it's like more of like verbally I say through that it's able to identify locations. Like it's quite good at doing that. I think it's because of the training data. So the training data itself contains like the locations of like the places. So therefore when it sees like the same like images, right? Or maybe like images that are similar places, right? It's able to identify the places that you're seeing in the data set. I don't think this is anything emergent, it's just an artifact from the training set.
I'm curious, right? What if you were to just include like an image of a different city? Like this case is New York, right? What if you just put like the Malayan there? What do you think you will like give out?
But because the prompt is just asking you for the caption, the response is the one talking about where's the location.
Yeah. So I had some thoughts about this about just to like better appreciate like what their work is trying to do.
Yeah.
Okay. So because it ties into the whole location thing.
Yeah, sure.
So right, you see that like they have video data that IMU.
Yeah.
And actually like in computer vision robotics, right? With video and IMU data, that's actually powerful enough okay, you have a robot, you have yes, an IMU and like a video recorder. It's powerful enough like this is called like SLAM, simultaneous location and mapping.
Okay, yeah.
Just these two modalities alone, the robot can reconstruct, can do 3D reconstruction and know where it is.
Yeah.
And I think that is why the locations is good because you gave it the raw data and hopefully like somewhere implicitly the transformer may have learned SLAM.
Oh, that's true.
Yeah,
that's interesting. Yeah, that's but I think the author didn't talk about it, but that's an interesting future work, like whether they're actually able to reproduce SLAM from just the training itself.
But in the first place, like in computer vision, like if you just have the video and IMU, people have been like trying to train models to do SLAM already.
Yeah. Oh.
Like to map stuff out and also know where your location is. So that's already like potential for the model to be able to learn.
Yeah.
So just like additional point to help you appreciate. Yeah, because like the whole IMU thing, which like if like it's actually very like centered in the robotics area. So like it's just weird.
But now that I think about it, I think they actually like inspired from SLAM because even in the appendix, right, they said that they do not use IM data directly. They always combine it with like a few frames of video or they combine it with image.
Yeah, because IMU like if you're not ironing by nature, it's just the 6 coordinates, 3 position and 3 angles.
Yeah.
But video, you have time series, so you can calculate velocity. And like because you're moving around, okay, that's like many different angles and stuff. Yeah. So yeah.
Oh,
there's a lot of potential for this.
Yeah. I think we need to open source this first, because it's been like, I think 10 to 20 days, they haven't really open sourced this yet. So I'm still waiting for them to open source.
Okay, anyone want to try to give a summary about the first 2 papers, how they're different from each other, what learnings make them contrastedly different?
Which 2 papers? Or like the first 2, not this one, right?
This paper and the previous one.
Oh, the Palm E, is it?
Yeah, the Palm E paper that Yuhong presented, right? Yeah.
Like this one?
Yeah.
Okay. So I think because for this one, right? Let me see. Yeah, I think there's a few like parallel places like this one where they say like the physio and the LLM, you cause it, will like if you train the LLM while you're doing all the pre-training, you cause the LLM to lose some language ability. I think the meta authors also said that this is also a case, that's why they froze it in the pre-training. So that's something that is like almost the same. But in general, I think there's still different tasks because this one focuses more on like robotics itself. While that one's more general. Like they just wanted one that like they're similar to more to like PentaGPT, which is able to like take in multiple modalities and not be used for like a agentic task, but more in just a general purpose generation of text. Well, this one I think is more towards like being used for the end case is being used for like a robotic training. That's why it's called. That's why they use it as an embodied like. This one they use like embodied. And another thing is that I think this one only trains on image and video, because let me find where is it. Yeah. So over here, they only use vision based. So like they only use image and vision modality. While that one is more general to audio, IMU data, and they of course they claim it can also do other forms of modality. But for now, the 4 main modalities they trained on was image, video, audio, and as well as IMU data. So I think it's also more general compared to Palm-E.
Okay, hold that thought.
Yeah.
We'll come to the next couple of papers, but I'd like you guys to all think about like, okay, if you add in another modality, which general architecture seems to make sense? And are there modalities that require specific treatment? Okay.
Okay.
Yeah, thanks, Warren.
Thank you. Okay.
Hello, hi everyone. Next, we are going to talk about NExT-GPT, which is a work from our fellow group, from Trust Group in US. So, and the good thing is this is an open source model. You have access, and there's a good demo for it. So their motivation to start with is that the limitation of the current multimodal LLMs is that they are good at understanding multiple modalities, like we showed earlier. It's able to take in embeddings inputs from different modalities and able to answer questions or do tasks. But they often struggle to produce content in multimodalities, in that if you have an image and you want to do something regarding the image, then it's quite difficult to do that. And therefore, they are trying to do this using an any-to-any multimodal LLM. And of course, their higher level picture is that humans communicate and perceive the world using different modalities. And it's quite natural that if the AI can do something like that. Yeah, so here is the general architecture. As you can see, because it's any-to-any, so it's able to take in text, image, audio, or video, or more modalities. They didn't experiment with that. Currently, it's just these 4 modalities. And the good thing is that it's able to produce content in these modalities as well. And there are several stages. I'm going to share them one by one. So the first stage is the encoding stage. And I would say it's very similar to the previous ones, where they fix the modality encoder. So if it's text, it just goes through the LLM. But if it's image, then it goes through an image encoder, audio encoder, or video encoder, depending on the modality. And these encoders are fixed. There's no training. And I think that they use the best encoders available for each modality. And the next part is about training the, like how do you align the embedding space. So they have different projection layers to project the modality embedding into the LLM's embedding space. So their way of doing that is through, I would say, simple alignment procedure, where we have a paired data. For example, for image data, we can have a paired set of images and text caption. And for audio, we also have caption, and for video as well. And then you go through the image encoder and get the representation. And this representation will be projected using a projection layer, and we will ask. So it goes through the after obtaining the image representation, it goes through the LLM and generates the image caption, and then the error compared with the ground truth, it goes backwards to the original projection. And that's how they train the embedding projection. And it's called LLM centric because the like the center of the everything is the big LLM, and the others are just serving this purpose. And for the next part, the center, the big LLM, is actually not big. I mean, in their actual implementation for now, it's just a 7 billion Vicuna model. And so the goal of this LLM is to taking any input and generate text plus signal tokens. So I think the signal tokens is a special novelty here, because they need to generate something. They need to generate something in another modality. So how do they achieve that? They put the tokens, the special tokens, and the special tokens will be sent to the different output layers later. Yeah, so I'm going to show you some examples. So for example, the signal tokens are like IMG1, IMG0 is just some special tokens, and the representation of these tokens will be sent to the different outputs. So for instance, when the user is asking, I'm going to summer, especially at the sea, I want to have some fun, then the LLM will first generate some text, and also it will generate the special signal tokens to show that we need to give an image, probably. So it will go through this image, the output projection layer, and this output projection layer will need to produce vectors for the generator. And here the generator is diffusion models, because you know that diffusion models are very strong at creating contents. So their goal is to find a good representation for the requirement, and then pass this to the frozen diffusion model to do the task. And because of the design, so it's able to process modalities from one to another. So for instance, so after it gives back a image, then the user say that, oh, I'm interested in surfing, and then provide the image on surfing. Then it goes to the LLM, and then the LLM even say that, okay, because the user asked, I want to create a vlog, and then the LLM even goes to create a video for the user. And yeah, there are many rounds. Like sometimes it can give you an image with the audio, and sometimes, let's say, if it feels that everything is just enough, then it just gives you a text. So there's a lot of flexibility and interaction here. And so on the right part, so how do they achieve this? It's like what I said. So they will send these special tokens, special representations to the output projection layer, and this output projection layer needs to be chained, and then it will go to the image diffusion model or other diffusion models. And so how do they chain the output side? So earlier we showed that on the input side you need some alignment. So on the output side you need some alignment as well. And here the way of doing it is also quite intuitive and simple. So given that we have an output response and the special signal tokens in each modality. Then it goes through the projection layer, and we have some embeddings or representations, right? And on the other hand, because we have paired data sets, so we will put the image caption or audio caption or the video caption into the text encoder of the diffusion models, and then we align these two spaces. So the overall motivation is just that now we have representations in the LLM space. Now we need to convert these vectors in another space, which is the diffusion models space. And then through this alignment data, then they're able to do the training. Yeah. And that was about alignment. And now, as you know, for a model to do well, especially in conversations or real chatbot interactions, usually you cannot just rely on alignment, and that's very primitive way of doing pre-training. But if you want to have a human-like conversation ability, you need to do some instruction tuning. And here is that they are doing modality switching instruction tuning. And there's not much detail about this part of the inside the paper itself, but it's actually a data set which contains 5,000 dialogues they created by themselves and using ChatGPT for some help. But the general idea is that they will first, so they have some output from the LLM and then some codon annotations specifying what's the most natural way of doing this. And then they will actually calculate the cross entropy loss between the text sequences, as well as the generated special tokens with the ground truth special tokens embedding in the diffusion models encoding space. So yeah, so overall is some other more fine-tuned ways of doing alignment where we can ask the model to be more human-like and able to do well on conversations and following instructions. So which is maybe not surprising that they gave very good results. So you can see that on most of the tasks, it's actually performing quite well. Although it cannot perform that well compared to the expert models in each domain, but since it's very general, so it's quite good. And yeah, actually their GitHub repo has around 2,000 stars already. It's quite popular these days. And another highlight of this method is that it's very lightweight. So in total, they only have the number of training parameters is only 131 million, which is I think even smaller than a bird. So it's quite small. And if you look at each part, it's actually most of the time is just training the projection layers. And for example, this is the projection layer from the encoder to the LLM, and there are different output projection layers, and of course the LoRa inside the LLM itself. So overall, there's not much to be trained, but it's more like an alignment and adaptation process of aligning different embedding space of different models and train them together. Yeah. And some analysis for the performance. This is, I think, from their own human evaluation. So they found that first of all, the model is better at generating the image image modality. For example, you see the text plus audio to image, and then plus so as long as the image is the goal of generation, then it achieves quite good performance. And it's also perform better at generating a single model output, meaning that if you ask it to generate both maybe image and audio and video, then it's very challenging, and the model is bad at doing that. Yeah, so overall, it's a very flexible framework, and since currently the model is still very small, so there could be larger ones ongoing in their group. So and yeah, so the good thing is there's a demo, and you can actually try it out. But since we don't have time here, so I put a link here, and you can click on their website, and it's functioning quite well, and you can allow you to upload an image or audio or video, and you can just interact with the chatbot online. That's quite interesting. I mean, because today we hear about many papers, but there's no interface to really test it, right? But here, this is working, and it's quite. So I recommend trying it out. Yeah, that's all for myself. Thank you. Any question?
Right. The part where you talk about the projection layer from the LLM projection layer, right? And from the input projection layer to the LLM, that's similar to like mixture of experts, because you have this signal token similar to like mixture of experts. You route the token to a specific expert based on like a different body. That will be something similar.
Yeah, so I think here in this case, the model also needs to decide whether it should go to that modality expert. So it has a similar concept of doing that. But I think they're not doing, they're just doing it in a very sequence to sequence manner. Meaning that they're not having a gating function to decide which route to go to. They're just, okay, just generate this token, then it means that this token should go to this modality. Yeah.
I have one question. Maybe you already said it, but so my question is, so how they train the model on all the tasks? Like they mix all the data of all the tasks together. Let's say the image, audio, video together, or they train the image first, then they train the audio.
Oh, that's a good question. I am not sure if. So the answer is I don't know, but I didn't remember reading it in the paper also, because this paper is more like a technical report where they are not sharing every detail of the architecture.
Yeah, I'm very curious.
But they depict some like so for like text plus text to text they use.
Yeah, but how they train it? They train the sequence.
Exact way they train.
I can they train that one first, then that
Like,
one.
The sequence of.
Do they have curriculum in the training?
But anyway, those are technical things. Just ignore.
I'm not sure about other models, like the previous models, if they also have different modalities, right? How will they train?
Yeah, but their different modalities are actually quite different from this one. So yeah, but this one like can take everything.
Yeah.
This is the first model where we see it's producing several different modalities, right? And it's using a control signal token to tell the model what it needs to produce a different modality, right?
Yeah. And we'll pass that signal token to the diffusion model,
right,
to do the generation.
And I think Long is right to ask about the curriculum. I mean, a lot of this is overlooked in a lot of papers, and I hope you guys all realize that the quality of the data, the instruction tuning, and the curriculum, those are all not really described too much. So you really have to infer a lot from their results to see which part of the paper is actually doing the bulk of the work. Like we already know in NLP, a lot of times if you just change your pre-processing pipeline, your results are wildly different, right? Because it happens very early in the system.
Yeah.
Okay, thanks, Tongyao.
Okay, then I will introduce the MotionGPT, and in this paper I think it's very interesting because it just treats the human motion as a foreign language and train the language model to apply in motion related tasks. And this paper was accepted in NUS 2023. And the background of this paper is that there are various motion-related tasks, but in most of the previous works, they treat the motion and language as separate modalities. So there are two problems. The first one is that they heavily rely on the paired data of motion and text to train the model. And the second one is that it can hardly generalize to unseen task or data. In this paper, they want to focus on two challenges of training the MotionGPT. The first one is that how to modeling the relation between the language and the motion. And the second is to build a uniform multitask framework to apply in various motion-related tasks. So the overview of this paper is that they leverage the strong language generation and zero-shot transfer ability of language models for the motion-related tasks. And they propose a three-stage training scheme. And two of the crucial parts is pre-trained language model on the raw motion dataset and user prompt tuning to fine-tune the model with textual description and motion dataset. After training the model, they can be applied into diverse motion-related tasks such as text to motion, motion caption, motion completion, and question and answer. So their methods, there are two key components of their work. The first one is the motion tokenizer, which converts the motion data to discrete motion tokens, and the second one is the motion-aware language model to understand the relations between the motion tokens and the text descriptions. In the motion tokenizer, they use the V2VAE as the backbone network to encode the discrete motion, encode the motion into discrete tokens, and then decode it to reconstruct the motion sequences. During this stage, they train with the off-the-shelf loss functions with reconstruction loss, embedding loss, and commitment loss. After that, we can map the human motion into a sequence of tokens. Then in the second part, they use the motion-aware language model to learn motion and language jointly. And in this paper, they just simply concat the motion, text and motion vocabulary into one vocabulary and use a transformer-based model to for conditional generation, and they use the loss function to maximize the log likelihood of the data distribution. And this part, the training of this part is actually follows the previous work in language model, and they do not modify a lot in this part. And finally, in the when we want to apply the MotionGPT into downstream tasks, they propose a three-stage training strategies. With the first two stage accomplished, they then fine-tune the model with specific tasks. So in the experiment parts, they compare with 4 downstream tasks about motion, text to motion, motion to text, motion prediction, and motion in between with previous state of the art, and showcase that they can achieve the best or competitive performance compared to others. And we can see that most previous works can only specific on one task, and the proposed MotionGPT can be applied into different tasks and still achieve very competitive performance. And here is several qualitative results. Actually, I don't know how to add the video into the slide, so only the figure is available here. They can use a prompt to generate motion sequences with which is better than previous works. And in summary, the contribution of this paper is threefold. They propose a uniform motion language generative pre-trained model named MotionGPT, and propose a motion language training scheme with instruction tuning, and propose a general motion benchmark for multitask evaluation. That's all about my presentation today.
Any questions about this work? Can you talk about the code book and the motion vocabulary that they introduced in their work? Do you remember any details about what they're doing for that?
Actually, I don't remember well.
Okay.
Yeah.
Anyone else have any questions? All right, so why don't we spend a couple minutes? Oh, it's already 21, so I think we better break, but I think it would be good for you guys all to think about what commonalities there are in these papers. Okay, what things are novel about each individual paper, and very importantly, because AI is going so fast, what remains to be done, or what's the next area. So right now, for example, you see that these methods are able to produce some output modalities, but they're doing it when prompted by a user. So you can imagine that a foundation model needs to choose a modality that's right to present information. But right now, the user gets to dictate, right? Oftentimes we can think about what's the right modality. Should I use a video, or is this better done in the picture, or is it better done in words, or because it's a noisy environment, I don't want to use audio. Okay, so these types of things we're not giving control over to the language model quite yet, but I'm sure very soon we'll see modalities that are either new modalities that don't exist currently because we confuse modalities together. Or we give control to the language model to be a proactive agent, right? So you may not have even finished your prompt yet, and the system will already have generated something for you, right? And interrupt you. Oh, did you mean this, or things like that? So this in dialogue is called mixed initiative, right? So you don't wait for the user to tell you something, but the system proactively asks, oh, did you mean this? Because I want to clarify what you want to. Right. So you can also think about the technical parts of this. I mean, it doesn't seem like there's a lot of interesting ways of dealing with multimodal quite yet. So I want you to think about, where there are various aspects of modality that's being encoded. So it's nice that we end up with this motion paper, because the motion paper is just treating it as a separate language to tokenize and things of this sort and quantize, right? But they've done it for this language, but in many other modalities, they're just treating it as an image, right? So they're taking a shortcut, say, well, it can be treated as a raster image, so I'm just going to do that as the most low-hanging fruit, right? So how much better could I do if I don't do that? But it's clear that a lot of these methods, they work pretty well for generation of images, because that modality seems to be fairly well trained. Okay, yeah, so thanks everyone. Sorry it's so late. We already knew that there were going to be a lot of papers today. Thank you. See you next week.
Let me get a microphone. Let me get it. Sorry, my converter was not.
No, it's not your fault. I had one, but it's just didn't work out at the end.
Okay.